It's a pleasure to be here. I will give you an overview of I would say, modern studies of the Hadron structure with a specific experimental tool that is Deep-Inelastic scattering. That is the most natural. When you take a complex object and you send a elementary probe in order to study the structure, let's say. Okay, what we are discussing is indeed this. My pointer does not work, so I will work with the pointer of the computer. So probably is without battery. But okay, we send an elementary probe, as I said, an electron against a complex object that the most natural we can imagine is the nucleon. Okay, that is the building block of the matter, and is also, I mean, a ballpark to study the strong force. So if you just measure the scattered probe, the pattern in the space of the scattered probe, you can access some global information of the structure of the nucleon that is parameterized in terms of Bjork and X, and that explain. Okay, that explain the fraction, if you want, the fraction of your target that you are, interacting with, and Q-square, that is the scale of the probe, so the energy of the probe you're using. You can do something more if you assume that the parton that undergoes the scattering fragments in a final hadron that you can detect, and you try to correlate the type of the hadron to the type of the quark, because what you can imagine that is pretty natural, that is more probable that the moment you start from a quark, you fragment into an hadron that have this quark as a valence. Okay, and you have not to have a more involved fragmentation to create different quarks. So this was done. And in Deep-Inelastic scattering, but also in other reactions, and provide some information of the number density of the quarks within your nucleon. We have a pretty, I would say, decent description of the unpolarized number density, and also polarized. In this case, longitude, the helicity one, that is along the momentum, that is essentially the direction that is defined by your probe. Okay, and you see some difference that the unpolarized are dominated by in the region of the C, where the Bianchi-X is small, while the ones that are dependent on the spin seems to concentrate instead in the valence, where X is large. And what is good is that together with the measurements, you can compare with the calculation in the lattice, and you see that they are basically consistent. These larger errors for lattice, for the unpolarized, is driven by the fact that you have to control this large contribution in the C. And this also explains why gluons are not really on top of the measurements, because, gluons are essentially generated, let's say, dynamically in the C. While for the spin, since the C is less relevant, the consistency seems better. Okay, so if we know how the partons are distributed in number inside the nucleon, what we can do? Well, we can do the calculations. We have a QCD, we do the calculations, and we try to describe the data. Things seems to work, but the problem is that this is true when you are in the perturbative region, so when the energy is large and your coupling constant is small. The moment that you move towards lower energies, your coupling becomes larger, and the calculations start to fail. Why we should be interested to do that? We don't stay in the large energy regime. The reason is that, yes, perturbative QCD works, and we are in a comfort zone there. We know what to do. But what we are interested is the non-perturbative part, because it's the non-perturbative part that describes the intimacy of the nucleon structure, okay? And what are the signals that we have something to learn? for example, we are not able to build up a budget for the spin. So the spin of the nucleon is the same of an elementary particle, but is generated by different contributions. So the spin of the partons, the spin of the gluons, the orbital motion of these partons, and we didn't yet understand how these conspire to create a spin that is the same of an elementary particle. Again, if we turn on spin, so we control polarization in initial state, we end up with a production of hadrons in the final state that is asymmetric in the space. So there is some correlation between what is happening inside the nucleon and what you observe in your world, in your laboratory, let's say. And this is also unexplained. Other examples, there are, I mean, I think you study in the textbook the form factors of the nucleon. And until, I would say, 10 years ago, the basic information was that the electric and magnetic form factors scale together as a dipole function, let's say. Then came new measurements that utilize the spin, so a transverse or polarization, and demonstrated that they're indeed completely different. And the methods used to measure before these form factor ratios were hampered by some instrumental effects. There was radiative effects. So a new knowledge came out that is pretty recently that demonstrated that we don't know so much about the nucleon at the end. And if you go to Q square equal 0, so you extrapolate back, an information you like to extract is the radius of the nucleon. And you can compare with other measurements, and you see that there is this proton radius problem where with different methods, you find different radius. Okay, so this is a topic quite interesting in these days. Oh, let's move again and go in another direction. So there are a lot of experiments that want to make collisions between heavy ions at high energy, trying to create these quark-gluon plasmas, famous quark-gluon plasma. One of the interesting outcomes was, again, that in the final state, they found, I mean, distributions, correlations, the hadrons that were not isotropic. And they relate this to the fact that when you have very complex objects that collide, they are not head-to-head. They can have collisions that are a bit on the side and create, let's say, elliptical flow or correlations, if you want, that then manifest in the final state. But the interesting part is that you don't need really ions to do that. You can do even with a proton, and you find the same things. So the proton is, this is something obvious if you want, as complex as an ion. It's really complex, and we don't know it. How we can access all this degree of freedom within that, and study, here is just a slide to show you that there's many different topics that you can study at that point, okay? But it's clear because, I mean, you have a peculiar dynamic that is not like all the other forces where you have a really, you can follow an approach that is perturbative. You consider just the leading term and you forget all the others. Here is not the case. You have everything that is conspired together, okay? So it's a rich phenomenology, pretty complex, unfortunately, but also pretty rich. So what we can do? So the approach is now to make a further step and not only measure the type of the hadron, but also the kinematic at the final state, okay? And pretend that the kinematic that you measure is related to the pristine kinematics of the parton within that confined object. In this case, then you turn on the information of the transverse momentum of the hadron with respect, everything here is calculated with respect to the probe that you are exchanging, that is this virtual photon, okay? So you care about the transverse momentum with respect to this direction of the probe, and then you care about the angles at which the hadron is created, and the eventual of the potential angle that you insert in your experiment, that is polarization of the target, if you really have it, okay? So this is the game now. We have our probe, high energy probe, that define the direction with the scattering plane or our lepton, let's say. And this was I mean, the basic tool that we all study in the books, right? Forget about the transverse degree of freedom because they are frozen by this high energy probe. But then the point is, are you studying the confined object or are you studying the interaction of the high energy probe? This was the question, okay? So now the focus is, let's study instead the transverse degree of freedom. These ones are living at the confinement scale and can provide us some information. So what we were able to do so far is to correlate this that is given by the Bjorken X, is there all the times, is the probe you have, with a transverse degree of freedom that in this case will be the transverse momentum of the parton, okay? This is this branch of a generalization and lead to the transverse momentum dependent parton distribution function. There is another one that correlates the X with the transverse position of the parton, that is the generalized parton distribution. I will not talk about those today. I will focus just on this for simplicity, okay? And this is a step forward to a global description of the partons with the nucleon. Let's say is the first step we are now trying to do. So is there only series to do something like that? No, of course. The series has the peculiarity that you have the distribution inside your target, the nucleon, and you have the fragmentation of the quark into the final hadron. These are, if you want, mirror phenomena, or if you want, correlators that described, I mean, this strong force dynamic in different, let's say, regimes, let's say. But you can imagine to make two hadrons colliding and look at two leptons in the final state. This is a Drellian process. In this case, you will have twice the parton distribution function. Or you can go on the other side. You have two leptons that collide and produce two hadrons. In this case, you will have two fragmentation functions, okay? And then you can also create more complex systems. But what I would like to show you, there are many laboratories that intend to do this kind of measurements, but CDIS is really, let's say, is a good compromise because it's clean and also provide you all the rich phenomenology, okay? So let's move to some more detailed description. So you now take your cross-section. Your cross-section is not anymore X and Q squared dependent, but you have also the fractional energy of the hadron, that is Z. You have the transverse momentum, as I said, and the angles, the relevant angles, the one of the produced hadron and the one of the target polarization. And you see that you have several terms. They are 8. These are the leading terms. Okay, there are also sub-leading that are suppressed by 1 over Q. But let's fix the leading terms. What you see is like a sort of Fourier decomposition, simple Fourier decomposition. Then you just keep the terms that satisfy the symmetries. Okay, the ones that are not satisfy you don't take. And you end up with this 8. It's pretty general and generic decomposition of the cross-section. And what you notice is that there are modulations and there are dependencies on the polarization. This is longitudinal target polarization, transverse target polarization, and helicity of the beam. If you are unpolarized, you just focus on these two terms only. And with the polarization control, you can open access to all the other terms, okay? So first message is, if you wanted to do this kind of study, better you develop experiments that are able to control polarization. Otherwise, you just pick up limited information. Then, this is generic. Now, what we can do? We can apply factorization and describe the process as, again, a function that describes the probability to pick up a parton inside your target. There is hard scattering that you can calculate. And then the probability that this quark fragments into the final hadron. This can be done and allow you to describe that each of these terms that are called structure functions as a convolution. You have, of course, the conservation of the momenta. And then you have the Parton distribution that described the probability to find a given quark inside a nucleon, and the fragmentation. And what you see is that you have a convolution here, okay? You see again Bjorken X. Here Q square is there, but it's not written for simplicity. But you see again X that tell you, if you want, the fraction of the target that you pick up, the Z that tell you the energy of the final hadron. And then you have the transverse momentum you have in the target and the transverse momentum you generate during fragmentation. And these are convoluted each other. So what is the message here? That we have a formalist, but whatever you measure is an involved object. Because if you wanted to really access this information, you have to solve this correlation, this convolution. And so in principle, you have to measure a full phase space to solve it, if you really wanted to solve it. But this is impossible in an experiment. Okay, so however, what does it mean? That each of these terms provide us access to a specific correlator of quarks within our target, or a specific fragmentation of the quark in the final hadron. These are, again, the leading terms. For the fragmentation, there are others, but for the moment, we are concentrating on this. And you see that they are all independent. There is a correlator that takes into account the polarization of the quark and the polarization of the hadron that we measure. We can only measure the hadron, but I mean, the quark inside it can have its own polarization. And the two are independent in principle, okay? So the moment we move from the simple Bjorken X to the transverse momentum information, we get access to these correlators that provide information on the dynamic. So again, what is the game? The game is we want to move out from this region where transverse momenta and Q are pretty large, and you can calculate these things. You have the gap evolution for Q, you have a hard gluon emission for large KT, and you want to go in this region where, I mean, the calculation does not work anymore. The request to apply the factorization I just showed you is that you have an order in the scale. So Q is the hard probe and should have the largest scale. And then you have this transverse momenta that can be or should be smaller than that, just to have an order in your, let's say, calculations. And this is what we want, because Q is the hard scale, we don't care, but Qt should be at the scale of confinement, so we want small. Okay. And then you have a transient region where you may have a dominance of perturbative or dominance of non-perturbative, depending on the energy you're working in. However, some notes. So, okay, in order to study TMDs, we have to apply this request. This request is clear from the theoretical point of view, but in the experiments, it's more complicated, again, because you should decide which point satisfies this and which point does not. And what really means very much smaller than, okay? This is just qualitative, but quantitative is not clear. Also, this transverse momenta is not the one you measure, okay? Because you are in the theory here. It is these ones, the single ones. But you measure a convolution of the two. So not easy, let's say. And this is one of the most debate, let's say, element right now, because we have experiments, but the phenomenologist should decide which data to use. Then, this kind of, let's say, correlator are described by amplitudes that are not trivial. Okay, there is a non-trivial gauge invariance in these amplitudes, and as a matter of fact, there is a universality that is not the most simple you can imagine. We think there is a universality, but it's not so trivial. For example, there are pieces like this that is called sievers that change sign moving from series to Drellian. Okay, and then it's not clear if for more complex reactions where there are hadrons in the initial and the final state can still be factorized. this is not proven yet formally. And then this is related to the fact that the Q-square evolution is not the standard one you have, that is the glab. It's something different, okay? And has inside non-perturbative elements that you can only extract from data. So rich phenomenology, quite complex interpretation. Of course, there is always a price to pay. But from this point of view, there is a lot to be done in the theory side. So let me start with some flashes. Number density of the partons. We started to have images of the nucleon and try to speculate again about the flavors, how they are distributed. You see here that we had a first hint a few years ago that the U were more concentrated than the D. Now more recent to do the opposite. Let's say the D is the green, is more concentrated than the U that is magenta, let's say. Then depends which fragmentation you are picking up. This is in pious, this is in chaos. But you see that we started to have, from all the data that we are collecting, not only cities, some means. If you don't consider flavors, you end up on a global average. Okay, clear. So there was shown a few years ago that, I mean, the moment that you move from this pinky average to, I mean, a more detailed information of the flavor, distributions, you may have a contribution that you need to take into account when you pretend to do precise physics with nucleons, like LHC is using protons, okay? And so if they wanted to do precise physics, they know to know what is inside, what can generate correlations to the final state. Otherwise, they will have an uncertainty. And the uncertainty was comparable to many others that theoretically they are considering, but they were forgetting this, for example, okay? Now, spin orbit effects. We turn on the spin now, and you see that the distribution is not anymore isotropic. There is an asymmetry there, okay? And this you may intuitively correlate to the fact that spin is related to the anomalous magnetic moment. Anomalous magnetic moment is correlated to currents, so to correlate movements of your partons within this confined object. And this is the science we have. These are the signs we have, that these things are real. They are not, I mean, really precise, because we are still in the initial stage. And you see here a tentative to demonstrate this change sign from series to Drell-Yan. This is what we have in real Drell-Yan. Or we have something like that when you use, when you produce a W that is pretty, twin, let's say, reaction. So you see that we have, I mean, indications, but we are still in the initial stage of the studies. Then, can you have correlators also in the fragmentation? Sure. I mean, what does the B factor? The B factory collide E plus E minus and then look what is generated in the final state, possibly a B meson. But due to the angular conservation, the E plus E minus react with a spin that is correlated, aligned. And this may, if there are these correlators I was speaking about, end up with asymmetry in the final state, even if you don't control any polarization in the initial state. And this is true. They found asymmetries in the final state, okay? So this provides you a sort of analyzer, because if you measure the final state, if the final state distribution is dependent of the spin orientation of the quark, then you have a method to measure the spin that the quark had at the beginning. And this enters the series, because, and this specific measurement, when you polarize the target, transverse to your probe, and you want to measure how many times the spin are aligned or not aligned with the target. This is the polarization of the quarks inside a transversely polarized nucleon that is called transversity. And you see that, yes, there is a sign that this effect is there. And is a convolution between this polarization of the quark and the fragmentation that manifests it in the final state. Why we care about that? Because this is a polarization of the quarks inside the nucleon, And is related, the moment you integrate along the Bjorken X, to what we call moments, and charges in this case. Okay, so you see here the integral of U, integral of D. Again, the comparison of what we get from data with what we get from lattice. You see that we are still far from data. Why so? Because essentially we cover just a limited range in X, and we need to cover large X and small X. The experiment done so far are just covering a limited X range. So the moment you integrate all the charges, you end up with a tensor charge. And the tensor charge is a fundamental property of the matter that is related beyond the standard model physics. So it's touching many other field of research. And so what we need is to extend the coverage in X. So I tell you many things. I tell you that there are a lot of correlators we want to measure. And so we have in front a formidable, I would say, challenge. Okay. What we can do? We can design new experiments, of course. So HERA, you know, was a Deep-Inelastic scattering collider, but wanted to go at extreme energies, looking for leptoquarks. Okay. Then you have fixed target experiments that typically lives at very low Q-squares. So what you wanted to do is to stay in the middle, because in the middle you can have access to the small transverse momenta, okay? And you, let's say, control the dilution that is given by the evolution, because the evolution essentially provide a larger Q-square, larger degree of freedom to dilute your signals. You want to stay close at relatively small energies in order that the transverse momenta you measure are related to your target and not generated by perturbative effects. So you don't need to go too high in energy. So you don't need to go really LHC. You want to stay in between, let's say, and possibly to increase instead the intensity to have a more, statistical precision. And this is the aim of the two facilities that are now, being realized. Let's say JLab at 12 is already existing, but the experiments are still starting, let's say, and the electron-ion collider is supposed to be the ultimate facility for these kind of things. Both of them are in the States. Okay, this is just for reference, are the kinematical variables. So let me now try to argue a bit what an experiment should how we, let's say, design the experiment and treat the data. So typically, an experiment, Deep-Inelastic scattering, has this distribution in X2². Unfortunately, the cross-section fall very fast with the Q², so the majority of the events are there. That means typically at the low X, but also a low Q², sometimes too low, okay? So the first thing you have to do is to put a cut. And typically there is this conventional cut, Q² greater than 1 GeV. That is not really high, okay? But it's conventional, let's say. And in this, you pretend to stay in the DIS regime. You don't want this tail. Then you have a cut, let's say, on W. That is essentially is the invariant mass of the hadronic system you are creating, and you want that it is large. Because if it is too small, means that you are creating 1, 2 hadrons. It's not really a fragmentation, okay? It may be dominated by specific channels you don't want. So you put there a limit. And then you have limits in Y that is essentially the fraction of energy that your probe put in the interaction. So if it is too small, essentially you have, in an intuitive way, you are transferring too less information from your probe to the virtual photon. So technically, the polarization of the virtual photon does not follow the polarization of your probe. So you're losing information. If it is too high, means that you lose energy, and possibly from other sources. Which other source? Radiative effects. If the probe is an electron, it tends to radiate photons, QED. simple QED. So when you have a strong loss of energy, it's may possible that it's not coming only from the interaction you want, but also from these radiations. So you tend to stay in the center, let's say, in this plane. And then about the hadron, what you want to do? Okay, transverse momentum, you want to catch as much as you can because you want to span from perturbative to non-perturbative. But in terms of Z, you have to take care to stay not too low, because in that case, you may enter the target fragmentation. You may have fragments of the target you don't want. And you don't want to stay too high, because again, in this case, you are concentrating all the energy in one hadron. And so you will end up in specific channels, not in a real fragmentation that is generic. Okay, so you should be careful to select your Z range. And then the approach is try to have a multi-dimensional investigation of all the relevant variables, because in this case, you can isolate the dependencies and the regimes. We discuss the leading or subleading terms as a function of Q. We discuss perturbatives against non-perturbative as a function of PT. The important thing is not to fold them together, but really distinguish, and so create a multidimensional analysis, X, Q square for the lepton, and then Z and PT for the hadron. The experiment then provides you typically not a cross-section, because it's difficult to measure on cross-section. Right? You have all the experimental effects. They tend to provide you asymmetries. So you take the difference, depending on some spin state, over the sum. In this case, most of the experimental effects cancel out, because they don't consider the spin. Okay, it's like the acceptance or your detector, something like that. But in this way, you wash out also some interesting effect that may provide you information for your extraction. So there is a price to pay. And then let me also point out that, okay, this cross-section difference you can simplify in a difference between the yields of event you have. But then you have to consider the polarization, okay? And the polarization enter here as a factor, okay? And reduce your statistical precision. And this is why it's so complicated to do these experiments. Okay, this is skip. Then you should care about the dilutions in your experiments. And I want to provide you a couple of examples. The first is really a kinematical one. When you calculate your hard scattering, you end up with some prefactors here. And these prefactors may enhance the sensitivity in some region or dilute the sensitivity in other regions. For example, this goes like Y. So when Y is small, I mean, your analyzing power is also small. And then look into these, again, asymmetries. You have the polarization of the beam, polarization of the target, but unfortunately, you should question, which kind of target can you have? Can you have a pure proton target? Almost. You can use hydrogen. Can you have a pure neutron target? No, sorry, you don't have. They decay. So you can use or deuteron, or for example, helium, and so you introduce unwanted, let's say, protons there. Even more complicated, can you use a hydrogen target, polarize it? No. In order to polarize it, you have to do to use other materials that are ammonia. And the moment you have ammonia, you introduce like that. You see that you have your hydrogen that you can polarize, but these are 3. And then you have 40 nucleons from the nitrogen that you cannot. And the majority of the events that you collect comes from these nitrogen. And you have to pick up, I mean, means that in this difference, only the 3 nucleon or the 3 protons of the hydrogen matters. But you see that on the denominator, you have also the nitrogen. And this is, again, a dilution of your signal. So we, as experiments, have an hard life in order to provide you data. And finally, there is also the radiative smearing that I speak about that tend to essentially move one event that was, I mean, originally in this, let's say, beam, and moves the event towards larger Y and move to another beam. So that event is a inter-beam contamination the moment we try to do this multi-dimensional analysis. And we have to unfold it. Then another small example. Typically, the experiment have a resolution that is constant in momentum because your spectrometer works to measure the momentum. But when you transfer this on the variables a phenomenologist wants, like Bjorken X, you have a non-linear effect. So a small, let's say, error in momentum in some region where Y is small becomes a large momentum in X. And again, you have smearing of the events on X. Okay, so we have to account all of that and also acceptance. So can we create an experiment that have 100% acceptance? No, we cannot. This is one of the precursors experiment, Hermes, that have, I would say, the majority of the first observation in this field. And you see the acceptance here was 2 arms separated by here this region where there was the beam. And so if I take an example of a scattering plane where the scattered lepton is, the virtual photon, yeah, I localize more or less there, and you see the hadrons that are produced around it, okay, with some transverse momentum and then some distribution in the angle. But you see also that we cannot pick up all the angles. And indeed, if we look to the 2 angles plane, the one of the hadron, the one of the target, we see that we have not uniform acceptance, and we have even holes there. And so this complicates our extraction. So in the last few minutes, I will show you what we can expect in the next future in this field. That is not easy. So there are 2 laboratories that are becoming the, let's say, next generation Deep-Inelastic scattering facilities in the States, JLab and BNL. So JLab has a 12 GeV electron beam that is circulating here and serving for holes, okay, that can be high polarized. This is an example of an experiment. The game is to try to see everything that came out from the target. Again, you see the distribution, x squared, the typical one. Also the coverage of PT and Z, the hadronic variables. The fact that it should be able to identify hadrons in the final state. And the fact that it should be able to use different targets and polarized targets in order to access different flavors. There are other experiments, but I mean, for the moment, I will concentrate just on class and show you some capability that we expect to have. These are, I mean, the comparison with what we get from the precursors experiments that are Hermes and Compass, the signals that I showed you before. And what we can have now at JLab, you see much more precision and coverage of the valence. That, if you remember, is the region where spin effects seems to dominate. So it seems to be really interesting. We want also to measure, I mean, the numbers of hadrons that are produced in the final state. These provide us information on the transverse momentum, the one that enters the unpolarized fragmentation function, the unpolarized, sorry, the function. But what I would like to show you is that here you may see some deviation from what you expect in that black points. And this seems to be real. And due to the fact that the energy is so low, you start to have effects of a phase space limitation in creating your hadrons. So there is speculation now to increase the energy of this facility in order to restore, let's say, the capability to study the full range in PT and also to extend the range in Q square. But in 10 years from now, what we hope to have is a collider. Collider has different problems, of course, but provide you a very flexible, let's say, environment, okay? This, in particular, wants to be able to move the center of mass energy, really to span, let's say, from perturbative to non-perturbative regimes. Okay, the projections is that I can pin down the errors pretty efficiently. I mean, the present knowledge, and then what we will have after this collider. The present knowledge is the green. What we're gonna have after the measurement is the blue, so we can pin down pretty well the errors. We will open also a new chapter, for example, jets. When you look to the leading hadron, okay, you have the fragmentation. But if you look to the jet is supposed to be everything that the fragmenting quarks produce. So if you collect the full jet, you have direct information on the quark. You don't pass through the fragmentation. You have direct access to the quark, and this will be attempted at EIC. And also you will have heavy flavors that you can study and are more sensitive to gluons. So new windows there. But let's come back 1 second. I told you that there are dilution in your kinematical prefactors. And if you compare the full cross-section that now has, again, Fourier decomposition with not only the leading, but also the sub-leading terms that are alloyed by symmetries, you find there are some terms that you better measure at JLab, and some terms that you better measure at EIC. So the two facilities will be complementary, just for the cross-section description. Okay. And again, the two will span a large Q-square range, so will allow you to span for, I'm done almost, from perturbative to non-perturbative, provide you, a way to study that limit that I was speaking about when PT should be smaller than Q. You will have a larger range where to study it. And you see that collider can span a very large phase space in X Q-square. The gray is what, let's say, we know today, and the color is what we pretended to know after EIC, let's say. Well, let me point out that it's so simple. The collider can do everything, and we are done. Let's wait 10 years then. No, it's not so simple. First of all, look here. There is a small corner that is not touched by EIC, but this is the valence. This is the valence, okay? This is logarithmic. And then if you want EIC to work in this regime, you see that the Q-square is pretty large. And I told you that typically you don't want too large Q-square, okay? So indeed, there was a study done that tried to understand, for example, when you do a phenomenological fit, you have parameters there, okay? So try to understand which, let's say, bins or let's say region in your phase space are more sensitive on these parameters, the one that people are using right now. And you see that for EIC, the sensitivity is there in the C. If you want to stay in the valence, you are so high in Q-square that you lose sensitivity. Why? Again, because you have so much energy that the evolution dilutes the original information of the nucleon. Everything you see comes from the perturbative QCD radiation. It's not the one originally the quark had, but it's the one that finally he got during the interaction. And so, but EIC has the capability to change the center of mass energy, as I mentioned. So this is the highest energy. Of course, you're exploring the C, essentially, the gluons. At the minimum energy, you are closer to the valence, but still not there. And for that, you need JLab. I can skip that. And so the conclusion is that we have evidence starting from 2005. The first evidence was 2005, so not much time ago, that these correlators are real. They describe the dynamic with the nucleon that then manifest in the laboratory. And now the real, let's say, challenge is to move from this first observation to a rigorous treatment, where you are able to pin down the evolution, when you become predict, and then you have to understand the terms of the evolution that are non-perturbative, because it's not a DGRAP. Then you need to introduce predictive power. And in this case, you have to control that you are universal in your distribution. And I told you there are examples that the universality should be generalized. So there is a lot to do. And from the experimental point of view, we are trying to create these facilities. Okay, and it's not an easy job, I can tell you. Indeed, JLab started in 2018. JLab at 12 GeV started in 2018, but the first measurement with a polarized target, that is what we want in this game, was 1 year ago. Okay, so even from the experimental point of view, there is a challenge. But this is the game, let's say. Big prize, but also hopefully, a big understanding. Thank you. Probably nothing is clear, but at least my intention was to provide you, I mean, hints. Then there are references there. You can maybe investigate with a bit more relaxed time these things. But from the point of view of the theory, they are quite interesting because they, I mean, you enter in an uncharted domain. You're not anymore working with DIGLAP. You're not anymore working with a simple universality. They are really, I mean, intriguing, I would say.